Section 1 Introduction. We're entering a new era in artificial general intelligence, AGI, thanks to large language models, LLMs. These models are showing impressive abilities in a variety of areas, including mathematical problem solving, programming, text generation, summarization, and creative writing. One of the key advancements in LLMs is the ability to align them with desired behaviors after their initial training, although this often relies on expensive human-annotated data. Common alignment methods include supervised fine-tuning, SFT, which uses human demonstrations, and reinforcement learning from human feedback, RLHF, which uses human preferences. However, these methods require a lot of human-annotated data. As a result, there's a growing interest in developing fine-tuning methods that can make better use of human data, making the alignment process more efficient. This leads us to explore how we can fine-tune LLMs without needing additional human-annotated data beyond the initial fine-tuning dataset. This is part of a broader goal in machine learning to transform weak models into strong ones without needing extra training data, a concept that dates back to the development of boosting algorithms. The question we're asking is, can we improve a weak LLM without needing additional human-annotated data? We believe the answer is yes. Drawing inspiration from the success of self-play mechanisms in games, such as AlphaGo Zero and AlphaZero, we propose a new fine-tuning method called self-play fine-tuning, SPIN. This method starts with a supervised fine-tuned model and allows the LLM to engage in self-play, eliminating the need for an expert annotator like a human or more advanced LLMs. In this method, we use the LLM from the previous iteration to generate responses to prompts in the human-annotated SFT dataset. The goal is to create a new LLM that can distinguish between the responses generated by the previous LLM and those generated by humans. This process is like a two-player game, where the new LLM tries to discern between the responses of the old LLM and human-generated responses, while the old LLM tries to generate responses as similar as possible to those in the human-annotated SFT dataset. The new LLM is obtained by fine-tuning the old one to prefer responses from the data over those from the old LLM, resulting in a distribution that is more aligned with the data. In the next iteration, the newly obtained LLM becomes the opponent for response generation, with the self-play process aiming for the LLM to eventually converge to the data, so that the strongest possible LLM can no longer differentiate the responses generated by its previous version and those generated by the human. Our method is similar to the recently introduced direct preference optimization, DPO, method, but with the key difference being the self-play nature of our method. This means our approach doesn't need extra human preference data, which is a requirement in the DPO method. Our method also resembles the idea of generative adversarial networks, GAN, where both the discriminator, main player, and the generator, the opponent, are instances of the same LLM from different iterations. We've proven theoretically that our method converges when the distribution of the LLM is identical to the target data distribution. Our experimental results show that while continued training using SFT on its own SFT dataset reaches a performance plateau or even diminished evaluation scores, our method consistently improves the LLM across successive iterations while using only a subset of the SFT dataset. In conclusion, SPIN effectively improves the base model's average score on the Hugging Face Open LLM leaderboard with significant improvements in scores on GSM-8K and Truthful QA, and on MT Bench. SPIN achieves results that are even comparable to models trained on additional preference dataset on Open LLM leaderboard and MT Bench. Our work is concurrent with other research that proposes the use of synthetic data with binary feedback in self-training, reducing the reliance on human data. However, our approach eliminates the need for additional binary feedback from humans or an extra reward model thanks to the self-play mechanism. In terms of notation, we use lowercase letters to denote scalars and lowercase boldface letters to denote vectors. We use n to denote the index set, 1, n. In the function space, let CF be the function class. The symbol Q_data designates the target data distribution, while P represents the conditional probability of LLM's response, i.e., LLM policy. Section Summary. Large language models, LLMs, have shown remarkable capabilities in various domains, but aligning them with desirable behaviors often requires costly human-annotated data. In this paper, we propose a self-play fine-tuning method called SPIN, inspired by self-play mechanisms in games like AlphaGo Zero. SPIN allows the LLM to improve itself by playing against its previous versions, eliminating the need for human or advanced LLM supervision, and our experimental results demonstrate its effectiveness in improving LLM performance. Section 2. Related work. Let's delve into the related work and the problem setting of this paper. Firstly, we'll discuss self-play. This is a learning method where an algorithm improves by playing against itself. It's been particularly effective in multi-agent reinforcement learning, where agents interact with copies of themselves, creating a progressively challenging learning environment. A key example of this is AlphaGo Zero, which used self-play to achieve remarkable performance against human players. Our work builds on this concept, using a similar self-play approach to transform a weak model into a strong one, without needing extra human-annotated data. As far as we know, we're the first to apply this method to improve large language models, LLMs. Next, let's talk about synthetic data for LLMs. When fine-tuning LLMs, human-crafted data has been very effective, especially for tasks like code generation and mathematical reasoning. However, getting enough high-quality human data can be expensive. That's why synthetic data, which can be generated by advanced LLMs like the GPT series, has become a popular alternative. Recent studies have shown that LLMs can rephrase prompts to improve their responses and augment synthetic data for more effective fine-tuning. Unlike previous studies that used more advanced models to generate synthetic data, our method generates synthetic data directly from the target model itself. Now, let's consider curriculum learning. This is a training method where data samples are arranged in a meaningful order, rather than being randomly shuffled. This has been shown to improve model performance. Initial studies in curriculum learning introduced efficient algorithms that progress from easy to hard. In natural language processing, criteria like sentence length and term frequency are often used. More recent developments have applied curriculum learning algorithms to multimodal learning. Our work shares a similar idea, where the training data evolves iteratively, starting with easy-to-distinguish responses and gradually progressing to more challenging ones. Now, let's set up the problem and go over some preliminaries. We're considering a large language model, LLM, that's parameterized by a variable we'll call b theta. The model takes a sequence of inputs, which we'll call xb, and generates a corresponding response, yb. In LLMs, each element of xb and yb represents individual tokens from a predetermined vocabulary. The model generates tokens sequentially for a given position, using only the sequence of previously generated tokens. This makes it a Markov process, where the probability distribution of yb given xb can be broken down into a product of conditional probabilities. Finally, let's review two major fine-tuning methods for LLMs: supervised fine-tuning and reinforcement learning fine-tuning. Supervised fine-tuning is used to adapt a pre-trained LLM to specific tasks, using a relatively small dataset of labeled examples. We consider a task where the prompts, xb, come from a specified distribution. The notation p_data represents the probability distribution of the associated high-quality responses yb from the training data. Supervised fine-tuning involves training the LLM to minimize the negative log likelihood loss associated with these distributions. The LLM after supervised fine-tuning is expected to generate responses that closely resemble those from the training data, significantly enhancing the model's performance for a specific task. Section Summary. The section discusses the concepts of self-play, synthetic data for large language models, LLMs, and curriculum learning. Self-play involves agents learning by playing against copies of themselves, while synthetic data is used as a proxy for human data to enhance LLM performance. Curriculum learning arranges training data in a meaningful order to improve model performance. The section also introduces supervised fine-tuning, SFT, as a method to tailor pre-trained LLMs to specific tasks by minimizing the negative log likelihood loss. Section 3.2 RL Fine-tuning. In Section 3.2, we discuss reinforcement learning, RL, fine-tuning, a technique used to enhance the specific abilities of general-purpose pre-trained models. This method is usually applied after supervised fine-tuning, SFT, to improve the alignment of language learning models, LLMs. In RL fine-tuning, we use a reward function that assigns a score to a given sequence pair. The higher the score, the better the response to the given prompt. The goal of RL fine-tuning is to maximize a specific function, which is influenced by the reward function and a regularization term. This regularization term ensures that the new model stays close to the reference model, preventing it from deviating too much and reducing the risk of mode collapse. However, the main challenge in RL fine-tuning is finding a good reward function. This usually requires training on a preference dataset, which can be resource-intensive to compile. It often involves comprehensive evaluations by human annotators or strong AI agents. In Section 4, we introduce a new fine-tuning method that enhances the performance of LLMs without needing additional human or AI feedback. We use a high-quality SFT dataset and a supervised fine-tuned LLM. We notice a quality gap between the actual response from the SFT dataset and the response generated by the LLM. This indicates that there's still room for improvement, so we propose using synthetic data generated by the LLM to enhance its performance iteratively. In Section 4.1, we introduce self-play fine-tuning, spin, a method that involves a two-player game. The main player's goal is to distinguish between responses generated by the LLM and those generated by a human. The opponent's role is to generate responses that are indistinguishable from human responses. Both the main player and the opponent are the same LLM, but from different iterations. The main player is trained to distinguish LLM responses from human responses. We formulate our objective function to maximize the expected value gap between the target data distribution and the opponent player's distribution. The value of the function reflects the main player's belief that a response originates from the data rather than the opponent's distribution. We also solve a more general optimization problem using a loss function that is both monotonically decreasing and convex. We choose the logistic loss function for its non-negativity, smoothness, and exponentially decaying tail. This choice helps prevent excessive growth in the absolute value of the function. Our approach is similar to the framework used in Wasserstein Generative Adversarial Networks, WGAN, but differs in the choice of the function class and the training procedure. Section Summary. RL fine-tuning is a method used to enhance the capabilities of pre-trained models by aligning them better with specific tasks. It involves maximizing an objective function that combines a reward function and a regularization term. The challenge lies in finding a good reward function, which often requires training on a preference dataset. However, a new fine-tuning method called self-play fine-tuning, SPIN, is proposed, which uses a self-play mechanism to iteratively enhance the performance of the model without relying on additional human or AI feedback. Section. Updating the opponent player. Let's break down the complex process of updating the opponent player in a game scenario. We've previously talked about how we train our main player, which we'll call f_t+1, based on the opponent player's strategy, represented by a distribution p_b theta_t. Now, let's assume we've successfully optimized our main player to differentiate between the real data distribution, p_data, and the opponent's strategy, within a certain function class cf_t. Now, we'll explain how we update the parameters, b theta_t+1, of the opponent player. Here's how it works. When our main player is given two responses, yb and yb_prime, to the same prompt xb, it evaluates the values f_t+1, xb, yb, and f_t+1, xb, yb_prime. It then deduces that the response with the higher value comes from the real data distribution, and the one with the lower value is from the opponent's strategy. The opponent's goal then becomes to find a strategy that generates responses that the main player can't distinguish from the real data distribution. This is done by maximizing the expected value of f_t+1, xb, yb, while also ensuring that the new strategy doesn't deviate too much from the old one to maintain stability in the game. This is achieved by adding a Kullback-Leibler (KL) regularization term. This leads us to an optimization problem, where we aim to maximize the expected value of f_t+1, xb, yb, while minimizing the KL divergence between the new and old strategies. The solution to this problem is a new strategy that is proportional to the old one, but scaled by an exponential factor related to f_t+1, xb, yb. However, it's important to note that this new strategy might not belong to the space of all possible strategies. We hope that the solution can be realized by a strategy with parameter b theta, meaning that the new strategy equals the solution. Solving for this gives us a relationship between f_t+1, xb, yb, and the log ratio of the new and old strategies. This suggests a function class for f_t+1, which is the log ratio of the new and old strategies, scaled by a factor lambda. Given this function class, we can find the parameters for f_t+1 that give us the desired log ratio. Substituting this back into our solution, we find that the new strategy equals the solution. In other words, the parameters learned from this process are exactly the ones we need for our ideal opponent. We can combine these two steps into a single training objective with an update rule for the opponent's parameters. This objective is defined as the expected value of a certain function of the log ratios of the new and old strategies. We summarize this iterative self-play process as follows. The opponent's strategy from the previous iteration is used to train the main player in the current iteration, resulting in a new strategy parameterized by bθ_t+1. We then choose the next opponent's strategy by copying the new strategy, which is then used to train the main player in the next iteration. This process is similar to direct preference optimization, DPO, for reinforcement learning fine-tuning. However, there are significant differences. Our method is applied to supervised fine-tuning and relies solely on the supervised fine-tuning dataset, represented by pairs, XB, YB. In contrast, DPO is designed for reinforcement learning fine-tuning and requires a preference dataset, represented by XB, YB_W, YB_L, where YB_W and YB_L denote the winner and loser responses, respectively. DPO requires that, at the instance level, YB_W is superior to YB_L. In comparison, our method requires that, at the distribution level, the target P_data should be distinguishable from the weak strategy P_bθ before it becomes a strong one. In terms of algorithm design, DPO implements a single iteration approach, while our method facilitates an iterative self-play strategy. Section Summary. In this section, the authors explain how they update the opponent player in their method called spin. They first describe how they optimize the main player to distinguish real data from the opponent player's distribution. Then, they introduce an optimization problem to find a better opponent player that generates responses indistinguishable from real data. They incorporate a regularization term to stabilize the self-play process. Finally, they present the end-to-end training objective and the iterative self-play process of their method. Section 5. Theoretical Analysis. In this part of our discussion, we delve into the theoretical aspects of the algorithm we've been discussing. We make certain assumptions about the objective function, which we denote as L. We assume that this function is both monotonic and convex. In simpler terms, this means that the function consistently decreases or increases and that it has a single lowest point. If these conditions are met, we can say that the optimal solution is reached when the parameter, which we call bθ_t, generates a data distribution. Let's break down our assumptions. We assume that the loss function, L(t), decreases monotonically. This means that for any given value of t, the derivative of L(t) is less than or equal to 0, and the derivative at 0 is less than 0. Additionally, L(t) is a convex function, meaning it has a single lowest point. This assumption is valid for many loss functions commonly used in machine learning, such as correlation loss, hinge loss, exponential loss, and logistic loss. Based on these assumptions, we propose a theorem. If there exists a situation where the data distribution generated by bθ_t matches the actual data distribution, then we can make two conclusions. First, if the generated and actual data distributions are identical, then bθ_t is the global minimum of the loss function for any non-negative value of lambda. Second, if the generated and actual data distributions are not identical, then there exists a suitable value of lambda for which bθ_t is not the global minimum. This theorem suggests that under certain conditions, our method will naturally stop when the generated data distribution matches the actual data distribution. This indicates that our approach is effective in aligning the model's distribution with the target data distribution. Moreover, the optimization process only stops when the global optimality is achieved, i.e., when the model's distribution aligns with the target data distribution. For the logistic loss function, we propose another theorem that provides a more detailed characterization of the opponent player, which helps us better understand our method. If the ratio of the actual to the generated data distribution raised to the power of 1, lambda lies within the model space, and if b theta underscore t plus 1 is the global minimum of the loss function, then the opponent player at the next iteration is proportional to the product of the generated data distribution and the ratio of the actual to the generated data distribution raised to the power of 1, lambda. According to this theorem, the model update tends to increase the probability of b theta underscore t plus 1 when the generated data distribution is less than the actual data distribution, and decrease it when the generated data distribution is greater than the actual data distribution. This confirms that our method's optimization process naturally converges to the point where the generated data distribution equals the actual data distribution. The update of the opponent player is controlled by the ratio of the actual to the generated data distribution raised to the power of 1, lambda, which is regulated by the factor 1, lambda. A smaller lambda results in a larger change of the opponent player, while a larger lambda leads to a smaller change. Therefore, as the generated data distribution approaches the actual data distribution, increasing lambda enhances the stability of the model training. In the next section, we present an empirical analysis of our method. Our results highlight several key points. 1. Our method significantly improves model performance across a wide range of evaluation benchmarks by surpassing the limitations of SFT. 2. Even without introducing new human-annotated data, our method at iteration 0 achieves performance on par to DPO training that utilizes even more data. 3. Iterative training is a necessary component in our method as it surpasses the limitations of multi-epoch training. Section Summary. In this section, the authors provide a theoretical analysis of their algorithm under certain assumptions about the objective function. They prove that the global optimum is obtained when a certain parameter generates the data distribution. The analysis also shows that the optimization process naturally stops when the LLM's distribution aligns with the target data distribution. Additionally, they provide a more precise characterization of the opponent player in their method when using the logistic loss function. This characterization helps in understanding the optimization dynamics of their approach. Section: Model and Datasets. In this research, we use the Zephyr 7b SFT full model as our starting point. This model is a refined version of the pre-trained Mistral 7b, which has been further fine-tuned on the SFT dataset UltraChat 200K1 by Hugging Face. UltraChat 200K is a high-quality subset of the larger UltraChat corpus, which contains about 1.4 million dialogues created using OpenAI's Turbo APIs. We randomly selected 50,000 prompts from UltraChat 200K and used our base model to generate synthetic responses. We then used these responses for further training, following the optimization method outlined in a previous section. We used a method of iterative training, where we added synthetic data from the most recent iteration to the newly generated synthetic data. This resulted in a synthetic dataset size of 50,000 at the start, and 100,000 at the first, second, and third iterations. We trained our model for 2 epochs at each iteration. For evaluation, we used the Hugging Face Open LLM leaderboard, which includes 6 different datasets, each focusing on a specific capability of language models. These datasets collectively provide a comprehensive assessment framework, evaluating language models on common sense reasoning, multitask language understanding, human falsehood mimicry, and math problem solving. We found that our method, which we call SPIN, significantly improved the performance of our model. At the start, we saw an overall improvement of 2.66% on the average score. The improvement was particularly significant on the Truthful QA and GSM-8K benchmarks, with improvements exceeding 5% and 10% respectively. As we continued to iterate, we saw further improvements, although the degree of improvement gradually approached 0, suggesting that the model had reached a limiting point in the last iteration. We compared our method with DPO, a model derived from Zephyr 7b SFT full, trained with DPO on approximately 62,000 preference data. This data, the Ultra Feedback Binarized dataset, includes both chosen and rejected completions evaluated by GPT-4. We found that while DPO requires either human input or advanced language model feedback to determine the preference, making data generation a rather expensive procedure, our SPIN only requires the initial model itself. Moreover, unlike DPO, which requires new data source, our method exclusively leverages the existing SFT dataset. In our ablation studies, we examined the effect of synthetic dataset size and training epochs within an iteration. We found that the synthetic data used by Spin was effective compared to the SFT data, and that iterative training in Spin was necessary. We also performed additional evaluations on benchmark tasks distinct from those in the Open LLM leaderboard. We investigated the effect of varying training data size on the performance of Spin. We found that while Spin results in notable improvement with increasing training sizes, SFT on further epochs 2 and 3 fails to yield more than 1% improvement. Lastly, we also show the performance of SFT from Zephyr 7b SFT full on UltraChat 200K for one epoch. While self-play fine-tuning with synthetic data from Zephyr 7b SFT full effectively improves its performance, simply fine-tuning it again on the SFT data leads to degraded performance. Section Summary. The authors of this study use the Zephyr 7b SFT full model as their base model, which is derived from the Mistral 7b and fine-tuned on the UltraChat 200K dataset. They generate synthetic responses using the base model and iteratively train their model for 2 epochs, resulting in significant improvements in performance on various benchmarks. They compare their Spin method with the DPO method and show that Spin achieves comparable performance using only the existing SFT dataset, while DPO requires new data sources. Ablation studies demonstrate the effectiveness of synthetic data and the necessity of iterative training in Spin. Section. Iterative training versus training for more epochs. We're going to delve deeper into the comparison between iterative training and simply training for a longer period of time. We're particularly interested in how the performance in the first iteration stacks up against the performance in the second iteration. We're also curious about how extending the training time affects the test results. We've tracked the performance of our model, which uses the Spin method, over several epochs during the first iteration. The most significant improvement happens in the first 2 epochs, with only minor improvements in the following epochs. What's interesting is that Spin proves to be both robust and stable. Lengthening the training time doesn't hurt the performance, but rather keeps it at a fairly steady level. However, this suggests that there's a limit to how much we can improve performance within a single iteration, highlighting the need for iterative training. As the test results from the second iteration show, extending the training time in the first iteration doesn't match the performance achieved in the second iteration. We also wanted to see how Spin performs on a wider range of tasks. We tested it on MT-Bench, BigBench, OpenBookQA, and the Open LLM leaderboard tasks. We specifically chose tasks from BigBench Hard that would give us a more thorough evaluation. These tasks included causal judgment, which tests causal reasoning, sports understanding, which tests common sense reasoning, and formal fallacies, which tests logical reasoning. The results of these tests are shown in a table and a figure. The table shows the scores Spin achieved on MT-Bench and the BigBench tasks. The figure provides a more detailed look at how the model performed on MT-Bench for different types of questions. What we found was that Spin improved performance on a variety of tasks, not just the Hugging Face benchmark, without any major setbacks. In fact, on MT-Bench, the model that was fine-tuned using Spin even outperformed Vicuña 13 BV 1.5, scoring 6.57.